Hello and welcome to Network Theory. The topic today is on node and supernode analysis. The references which have been used from Ravish R. Singh, Circuit Theory and Network Analysis, William Haight, Electrical Circuit Analysis, and Charles Alexander and Sadiku, Fundamentals of Electric Circuits. These are the textbooks which have been used as references. So we are going to be discussing node and supernode analysis. Okay, now speaking about node analysis, it is based on KCL or Kirchhoff's current law, which states that the algebraic sum of the currents meeting at a point is zero. And this point is basically what is called as the node. So what is a node? Every junction where two or more branches meet is called as a node. So suppose you have a circuit like this, some kind of a circuit, where you have a voltage source or a current source, suppose, and something like this, and you have voltage source here. This is a node where you have got three branches meeting, right? So 1, 2, and 3. This is a node, and here two or more branches. So at least two branches should meet at this node. That is what is defined as a node. Now, one of the nodes in the network is taken as the reference node. So, reference node is basically, again, nothing but something which we choose as a reference. So, reference node normally is chosen to be at ground potential. So, you can refer to it. So, normally one of the nodes is chosen as a reference node. It's also called as a datum node, you can say, right? And with reference to this node, you're going to be writing the node equations. So if there are n nodes in the network, the number of equations to be solved will be n minus 1. So these are basically basic information regarding node analysis. Now, when we speak about node analysis, the steps involved are: first, assuming that the network has n nodes, you assign a reference node. So a reference node is assigned, like I told you before, and directions of the currents are defined or designated. Then you are assigning a current and voltage name for each branch and node respectively. So basically for the node, we call the node as the voltage as V1, V2, etc. and so on, currents I1, I2, etc. And apply KCL at each node except for the reference node. So you do not apply KCL at the reference node and apply Ohm's law to the branch currents and solve the simultaneous equations. So using these voltages, find the branch currents required. So basically node analysis is nothing but application of KCL only. Now the reference node can be any one of these symbols can be used for reference. Okay. So while doing a problem on node analysis, so you have a circuit here. So first thing what we do is always designate the reference node. So here this can, the logic says that this can be chosen as a reference node. Normally the maximum number of connections, common connections are here, and this can be designated as a reference node or zero potential. So total number of nodes, if you see, is equal to 3, which is 1. So how do you designate the nodes here? First node here, there are 1, 2, and 3 branches. So I'll call it as 1. Here, 1, 2, and 3. Again, I call it as 2. So the 1, 2, and 3. So total number of nodes is equal to 3. Now redrawing the circuit, you can name the nodes and mark the voltages. So marking the voltages, I'll call it as V1. This is as V2. Now, since these are all, this is one point, this is another point, and these are the two nodes, we can redraw the circuit and show it like this. Okay. So here we can see this is one node, this is another node, and this is the reference node. So marking out the voltages, I call this as V1, call this as V2, and this one is the reference node. Even if I do not mark the ground symbol, it is okay, it is understood, and this is your reference node. So there are three nodes, like we said already. Now, when I'm writing, so initially we'll start with writing KCL to node 1. Now, when you're applying KCL, KCL says that algebraic sum of the currents is equal to 0 or current entering is equal to current leaving. Now, the assumption when we write node analysis is that the junction or the node at which I write KCL, which KCL is written, is assumed to have higher potential. Have higher potential than all the other voltages. Right. So in this case, if I'm writing at V1, I consider V1 to be greater than V2. If I write an equation at V2, you consider V2 to be greater than V1, so that you can write the equation in that particular format, right? According to whatever what do you say? According to KCL. So now, if I'm writing KCL in node 1, what would be my equation? The current entering is equal to 3.1 ampere. Then this will be equal to current leaving. The current through the 2 ohm branch is V1 by 2, and it is going to be going like this, right? It is a leaving current, so V1 by 2. Then, since V1 is considered to be greater than V2, the potential like we said, so the current is going to be flowing out of node V1. So the current which is flowing through 5 ohm resistance is V1 minus V2 divided by 5. So this is our first equation which is written at node 1. Similarly, we write KCL at node 2. Now, writing KCL at node 2, what do we get? At node 2, we have got again 3 branches. So, again, if I write the expression of the current through the 1 ohm resistance, we have got a V2 divided by 1 plus. Now, again, V2 is assumed to be greater than that of V1 potential. So, it is V2 minus V1 divided by 5, right? And that is equal to, now, 1.4 ampere is also flowing out. So these all currents are leaving this terminal V2, V2 by 1, V2 minus V1 by 5, and minus 1.4. So minus 1.4 is equal to 0, or I can write it as equal to 1.4. Minus 1.4, which is leaving, can be considered as a 1.4 entering this terminal, plus 1.4 entering the terminal. So current entering is equal to current leaving. So you've got two equations, and you can solve this and find out the values of V1 and V2. The main point is how to write the equations. So once we write the equations, we can solve. So the question was to find out the voltage across the 5 ohm resistor. Now, since V1 is found to be greater than V2, so V1 is 5 volt and V2 is 2 volt. So if the voltage across the 5 ohm would be V1 minus V2, which is 3 volt, right? So this is how you are solving the equation using nodal analysis. Now, so let's write the equations for this problem. Determine the current through the 5 ohm resistor for the network shown. So this is the 5 ohm resistor, and we are going to be solving the equation. So let's just write the current equations by applying node analysis. Now, again, we can see here there are V1, 2, 3. So here the reference node is already shown, and here we have got totally 1, 2, 3, and 4. So for total number of nodes is 4, but you're going to be out of which your one node is a reference node. So you've got n minus 1 equations. So n minus 1 equations correspond to 4 minus 1 or 3 equations, which is obviously understood because we have got 3 unknowns, V1, V2 and V3. Now let's write KCL at V1, at node 1, right? When we are writing KCL at node 1, what do we have? So here 3 ampere is flowing in, and always assumption is that V1 has a higher potential. So with this assumption, current entering 3 is equal to current leaving, which is 1 is V1 divided by 4. Second branch is V1 is 2 ohm. The current through the 2 ohm will be V1 minus V2 divided by 2. And the third branch is here. Now you can see that there is also a voltage source. So you have to consider the effective potential across a 4 ohm. So 4 ohm has a potential drop of V1 minus 36 minus V3 divided by minus V3 divided by 4. This is our third branch equation. So again, the assumption is V1 has a higher potential than V3 or than 36. So I mean, this is 36 volt. So you have to go from here. The main assumption being that the current flows out of V1. So V1 and following the current direction, it is plus to minus has a drop in potential. So it's considered as minus 36 and then minus V3 divided by 4. That is the total potential drop. Similarly, writing for node 2 equation would be this. So node 2 has got 3 branches. There is no current source here. So node 2 equation, this is node 1 equation. So node 2 equation would be what? V2 divided by 100 plus V2 minus V1 divided by 2. So here again V2 minus V1. V2 is considered to be at higher potential. Now next one is 5 ohm plus V2 minus of V3 divided by 5. Now all these currents are leaving. There is no current which is entering, so is equal to 0. So the last is at V3. So at node V3, what do we have? The last equation, which is to be V3 divided by 20 plus V3 minus V2 divided by 5. So we are speaking about this 5 ohm, this 20 ohm, and the last one, which is this branch, right? So this particular branch. So when we are writing for this particular branch, so now going from V3 towards V1, so V3 minus to plus is a plus. So V3 plus 36 minus V1. So this is how we are going to be writing it. So the effective potential drop is going to be V3 plus 36 minus V1 divided by 4. And again, V3 does not have any current sources. So all the currents are again and leaving. So that is equal to 0. So we have got 3 equations again now. All these equations, we get the values like this. We can you can solve these 3 equations. You can use your calculators to solve the simultaneous equations. And the current through the 5 ohm resistor is given by V2 minus V3 divided by 5, because obviously the voltage across the 5 ohm resistor is given by V2 minus V3. Now V2 is greater than V3, so it's V2 minus V3, and the current will be divided by 5. So the current is got as 3.11 ampere. So this is how you write the equations in a node analysis. Now coming to something called as a super node. So nodal analysis, when there are voltage sources in between reference nodes, that is called as a super node. So what is a super node? When a voltage source is connected between two non-reference nodes. When the voltage source is connected between two non-reference nodes, a super node is formed. So in this case, you can see that there are two nodes V1 and V2, which are non-reference nodes. Non-reference means they are not at ground potential. This is a reference node. So V1 and V2 are not non-reference nodes. And you can see that there is a voltage source between them. So when there is a voltage source, the problem is that you cannot write the current equation. So you do not know how much is the current through this branch. So KCL is difficult in this branch. So we call this as a super node. So whenever there is a voltage source between two non-reference nodes, it's a super node. And at the same time, we can also see that if the circuit is these sources can be either dependent or independent. So it does not mean that it has to be a independent source only. It can be a dependent source also. So between these non-reference nodes, then it is treated as a super node. So what is a super node? These terminals, the voltage source, and if anything is connected in parallel to it. For example, in this case, you have a 10 ohm connected to it. So this much, the whole part is considered as a super node. So if the circuit has any dependent or independent sources, so a voltage source connected between two non-reference nodes, a super node is formed by enclosing the source, its terminals, and any elements connected in parallel with it. That is what. So any elements are connected in parallel, which means in this case, the terminals, the voltage source, and this element is called total supernode, right? So here the 2-volt source is between the two non-reference nodes 1 and 2. So this much, this total is called as a supernode. Now, how do you do the analysis of a supernode? Let's see. When we speak about analysis steps, the first thing is that at a supernode, we have to identify the supernode, so which is formed by enclosing the source, terminals, and any elements connected, as we said already. First, identify the supernode. Write the voltage equation for the supernode. Why? Because at the supernode we have got a voltage source. So in the previous case we had there was a voltage source in between. So the plus minus or whatever you had between these two nodes, you had a voltage source, right? Now I am not able to write the KCL here, but I'll write KVL here, which means suppose if I have a 2 volt here, I can write V1 minus V2 is equal to 2 volt. This equation can be written. So write the voltage equation for the supernode using normal KVL. Then apply KCL to the supernode. So here, once we have written this, apply KCL to the supernode by considering both the nodes at the same time. Now, which means what? Once I have considered this, after this, you are not going to be considering this, but you're going, because this is already considered here as a KCL. Now, after that, you can have some many branches coming over here. So write the branch currents using normal KCL. So write the node equations at node 1 and node 2 at the same time. So in one equation, you are going to be writing instead of two separate equations. Normally, we write two separate equations at node 1 and node 2. Instead of that, you're going to be writing one simple equation in one simple expression or one equation only for both the nodes. Okay, now understanding this with an example. So if you see here, the super node which is there, you have between two non-reference nodes, V1 and V2, there is a voltage source. So this is a super node. There is also a 10 ohm resistance which is connected in parallel to it. So 1, 2, this voltage source and the 10 ohm, this forms a super node. And when you're writing the super node equation, you are going to be ignoring the value of this 10 ohm resistance, right? And when you're writing KCL also, you do not consider this. But it is not that we ignore it completely. We'll write the equation for the we'll write the equation for that voltage source as equal to V1 minus V2 is equal to minus 2 volt. So between V1 and V2, we have got a minus 2 volt. So we have written, so this is the KVL equation. Now let's write KCL equation. So one equation is a KVL which has taken care of this voltage source, because we cannot anyway write KCL for this branch. So for the remaining branches, you're going to be writing KCL. So how is the supernode equation written? Supernode equation is written by considering both the nodes at the same time. So if I write both the nodes at the same time, by ignoring the minus 2 volt and the 10 ohm resistance, because those are forming the supernode. So this is ignored, and remaining branches you're going to be writing KCL. So I get an equation like this: V1 divided by 2, V1 by 2 minus 2 plus V2 divided by 4 plus 7 is equal to 0. So this has been written considering that this is V1 by 2, current flowing out. There is a current flowing in which is 2 ampere, which I am writing it as minus 2, right? And V2 divided by 4, which V2 by 4 is a current. So you can see that I've written we have considered both the nodes at the same time. So this much was for V1 and this much is for V2, and we are considering it in one equation, right? Except for the supernode. So supernode equation has already been considered here. That is, the KVL equation has been considered here. But this is the KCL equation. So here KCL for supernode. And the supernode is going to be like this. And if you had now see that we have not considered the 10 ohm resistance here. Now, even if I had written the current for the 10 ohm also, it gets cancelled. So how do I explain that? If you see, if I write, suppose I consider the at V2, the current through the 10 ohm is V2 minus V1 divided by 10. Also at V1, it is V1 minus V2 by 10, and that is equal to 0. So again, if this is considering the 10 ohm resistance also, so we can see that this gets cancelled. These two get cancelled out. So effectively, V1 minus V2 and V2 minus V1 by 10 is coming in the same equation, because of which it gets cancelled. So which means that you can say that this is redundant, or effectively, since it is in parallel to the super node, and the super node, when you're writing KCL, the so for the super node, that is why we were saying that the 10 ohm resistance is getting ignored, right? So even if you do not write this equation, it is fine, and if you write it also, it will automatically get cancelled, provided you write it properly. So this is how we write the super node equations. One will be a KVL equation for the voltage source, and the other will be KCL equations. Fine. Okay. So now we have another problem here. So here, in this case, if you see, again V1 and V2, there is a voltage source in between this. So in between V1 and V2, there is a 6 volt. So V1 and V2 are forming a super node, right? So the super node is V1, V2, and the 6 volt, right? So here we can write that V1 minus V2 is equal to 6. That is the first equation we are going to be writing it here. Now, the other point to be noted is that there is a, here there is an 8 volt source, right? There's an 8 volt battery between V2 and V3. Why are you not considering, these are non-reference nodes still, but you are not considering this as a super node? Why? Because there is a 7 ohm in series in this branch. I can always find out the current through the 7 ohm as equal to the potential drop divided by 7 will give you the current. So as long as KCL can be written through a particular branch, this is not going to be considered as a super node, right? So super node is where you are having only a voltage source. The resistance can be in parallel to it, that is fine, but it is not to be in series with it. As long as you can find the current through this resistance, it's not a super node. So having clarified that, now let's write so the super node KVL equation has been written here. This is KVL. So now let us write the KCL equations. So when we are writing the KCL equations at node 1, we have got 1, 2. This is, so only two branches are there. So 2 ampere is flowing in, and there is this branch. Current through the 4 ohm is V1 plus 5 divided by 4. This is at V1. Similarly, at V2, you've got 1, 2, and 3 branches. So we are going to be writing, when we are writing the super node equation. So what is the super node equation? Super node KCL equation is going to be considering 1 and 2 at same time, right? So when I'm writing this, at node 1, we have got a 2 ampere current which is flowing in, right? And this current is flowing out, this current, the current through the 4 ohm resistor is flowing out, this current is flowing in. So when I'm writing it is V1 plus 5 divided by 4 minus 2, because the current 2 ampere is flowing in, right? That is, I've considered it as minus 2. Now V1 node is considered. Now coming to V2. So 3 branches are there. So let's write the equation now. At V2, there is at this branch, through the 10 ohm, the potential drop is going to be V2 minus 2Vx divided by 10. So that is a dependent source, but you do write the equation like this, divided by 10. So consider this. So this branch is considered. Now the next branch is this one, V2. So here it is V2 minus V3 divided by 11. And the third branch is here. So here the equation would be, considering that V2 is at higher potential. So V2 minus 8 minus V3 divided by 7. This is equal to 0. So this is our equation which we are writing. So we have considered uh, this branch, and this branch. 3 branches at V2, 2 branches at V1, except for this between branch. So this has been considered in this equation, right? So now how many equations have we got on till now? We have got two equations, 1 and 2. There are 3 unknowns, so 3 equations should be there. The third equation is at V3. V3 is not a super node, so normal KCL. So at node 3, we have a normal KCL, which we are going to be writing. So V3, there is a 12 ampere flowing out, then this current and this branch. So let's write V3 minus V2 divided by 11 plus this the 12 ampere which is flowing out plus 12 and plus V3 minus of V2. Now see here, we are going in this direction because V3 is supposed to be higher potential. So V3 in this direction, if you are going, V3 minus 2 plus is a plus. V3 plus 8 minus V2 divided by 7. This much is equal to 0. So all the sum of all the currents leaving this, this and this all are leaving. So sum of this is equal to 0. So we have got 3 equations. Again, you can solve it. You are asked to find out Vx here. Now see, Vx is the voltage across V2 and V3. So Vx is nothing but you can write it as Vx is equal to V2 minus V3. So once you solve these equations and find out V2 and V3, you can find out Vx as equal to V2 minus V3, right? So for the main thing is writing the equations. So super node equation we have written by considering the voltage source using a KVL, and the remaining at the super node there will be a KCL, one KCL equation considering both the nodes at the same time, and the third equation is not a super node, which is normal KCL at node 3, right? So you have got 3 equations in this case. There are 3 unknowns, V1, V2 and V3, so 3 equations are there. This is how we go about it. So the summary of node and supernode analysis is that nodal analysis, basically application of KCL at non-reference nodes. Non-reference nodes are at non-zero potential, and between two non-reference nodes with a voltage source in between, we have a supernode, right? And the supernode is basically something like this. When you have a voltage source, suppose a voltage source in between two non-reference nodes, and if there is some resistance or some element in parallel to it, so that can also be ignored. So this V1 and V2, so this voltage source, these terminals plus this resistance are the wholly form the supernode. You are going to be ignoring this when we are writing KCL, but we'll write a KVL. So when we write a supernode equation, one is a KVL and the other one is a KCL. KVL for the voltage source. So you are basically considering the voltage source, contribution of the voltage source by KVL, and KCL will take care of the currents. So whatever branch currents, so the remaining part of this, except for this part, this is going to be ignored, and all the other branches you're going to be considering to form the KCL equation. But at the same time, when you're writing the KCL, both nodes at the same time. At same time, not different equation in one equation. This is what you're going to be writing. So there is only one equation which you are going to be writing for KCL, which considers both V1 branch currents and V2 branch currents at the same time. And when you're writing that KCL, you do not consider the voltage source, obviously the voltage source, and if there is a resistance parallel to it, that is also ignored while you're writing the KCL. Right. So this is a summary of node and supernode analysis. Hope you understood. Thank you. And we'll in the next video we'll discuss about mesh analysis.